Okay, thank you, Alan and Johanna. Thanks for inviting me. I'm happy to be here, so to speak. So today I'm going to talk about finding Laurent polynomial mirrors to Fano Quiver flag 0 loci. So I've written out the plan of what I'm going to talk about. So I'm going to spend the first part of my talk talking about why Quiver flag 0 loci and why mirrors, and then I'll talk a little bit about A side in this perspective, I guess, and computing the quantum period. And then the main part of my talk will be about actually finding the mirrors, and that's going to be about, I'll talk about generalization of the Gelfand-Cetlin toric degeneration of the flag variety to certain Fano quiver flag 0 loci. So please let me know if you can't hear me or you can't see what I'm writing or anything. So first motivation. So when all my Fano varieties are going to be smooth and over C. And so then what makes it possible to talk about Fano classification is that there's only finitely many n-dimensional Fano varieties up to deformation. And this is due to Colère, Miyaka, and Mori. But it's not constructive, which means it's a separate question to ask what exactly are they. And so in dimension 1 and 2, this is classical. And in dimension 3, there's 105. And this was major work due to Skuzki and Mori Mukai. And so then after this classification, after the fact, it's been shown that all of these Fano varieties have a very particular structure. So all our construction can be constructed in a particular way. So all dimension less than 3 Fano varieties can be constructed as the 0 loci of sections of a certain vector bundles, which I'll say more about in a second, of GIT quotients of vector spaces. So this section here is a section of a vector bundle that you get by taking another representation of G, which I'll call E, and plotting it with the semi-stable locus of V, and then taking the diagonal quotient of G. And I call this a representation theoretic vector bundle. And I'll usually denote it, e.g., the vector bundle coming from this way. And in fact, you can be a little more specific. About what these Fano varieties can be constructed as. So all of these dimension less than 3 Fano varieties can be constructed as either toric complete intersections which is when the GIT quotient of the toric variety and G is the abelian, or as quiver flag 0 loci. And these will be the focus of my talk. And this is when V mod G is a quiver flag variety. Ambient space is a quiver flag variety, and the subvarieties are called 0 loci. And then this is, in particular, G is not abelian. I'm not saying all GIT quotients that are not abelian are quiver flag 0 loci, but some are. So these tend to be, toric complete intersections are well understood from the perspective of the mirror symmetry constructions I want to talk about. And these are sort of the next generalization you might be interested in. And so the theme of my talk is going to be that if you're trying to think about a Fano variety of type 2, it's productive to try to reduce it to type 1 because those are easier. And there's two ways of doing this. One is via Bayesianization, and one is via toric degenerations. And both of these will come up today. So before I go on and tell you a bit more about the motivation, I just want to define to you what quiver flag varieties are and what quiver flag zerolos are, so you know what I'm talking about. So quiver flag varieties. So these are constructed by taking a quiver Q, and it's an acyclic quiver with a unique source. So we can take Q0. So I'll write the quivers, Q0, Q1, and these are the vertices. These are the arrows. And then it's acyclic, so we can pick a labeling of the vertices, say from 0, 1 to rho, such that all the arrows go from the left to the right in this order. And so the 0 here is the source vertex. So that's the quiver. That's one piece of information input you need. And then the other input is the dimension vector. So this is a choice of dimension for each vertex, but we always choose dimension 1 for the source vertex. And then the group defining the GIT quotient is the product of the GLRIs, and the stability condition defining the GIT quotient I'm going to take is 1, 1, 1, and the character group of G. So then this GIT quotient right here is called the quiver flag zerolos, quiver flag variety, sorry. And this is the quotient of all the representations of the quiver of the given dimension vector by the group G with the stability condition. This is the label, and this is a quiver flag variety. So for example, if you take this quiver here, first just write 1 with row vertices, and I'm going to write the dimensions below each vertex. So this one has dimension 1, this one has R1, has a row, and then if you have n arrows from the source vertex to the last to the next, and then 1 arrow between all the other vertices, then the quiver flag variety you get is just the flag variety of n-dimensional quotients of dimensions R1 to R0. And in general, quiver flag varieties share some of the properties of flag varieties. So a quiver flag variety is a smooth projective variety. It's a fine moduli space for theta stable representations of Q. It's a Morey dream space. And it's a tower of Grassmannian bundles. And these are all due to Craw, who introduced quiver flag varieties. And then one last property of them which we'll need is that you can write them just like you can flag varieties as the zero locus of a section inside a product of Grassmannians. So here, this is a product of Grassmannians from I equals 1 to rho, and this SI tilde is the number of paths in the quiver from the source to your ith vertex. And I could tell you what this section is explicitly, but it's not relevant. We can just think of it as giving incidence conditions, cutting out the quiver flag variety inside the product of Grassmannians. And so the actual Fano varieties that we're interested in are not quiver flag varieties so much as quiver flag 0 loci. So these are subvarieties cut up by sections of representation theoretic vector bundles. And these turn out to look like, if you take the vector bundles, which are given by the restrictions of the tautological quotient bundles on this product, we'll put back to the product. Or you could think of these as the universal bundles, coming from the fact that this is a more fine moduli space. Then the quiver flag 0 loci are 0 loci of sections, where the sections are sections of vector bundles that look like direct sums of tensor products of Schur powers of these tautological quotient bundles. So those are the what you need to know about quiver flag 0 loci, the second type of Fano varieties that show up in the dimension less than 3 Fano classification. So if you want to start classifying in dimension 4, it makes sense to start by classifying Fano varieties of type 1 and 2. Maybe they're most of them or all of them, but at least it should give you a sense of the landscape. And in order to make this a finite problem and computer accessible, so it's not really classifying, what people have done is to restrict the ambient space to dimension less than 8. And then you can enumerate and walk over all dimension 4 Fano subvarieties of type 1, which was done by Coates, Kasperchuk, and Prince, and of type 2, which was done by Coates, myself, and Al. And so there's 141 here that don't fit into the previous searches, and these are the ones I want to talk about as a testing ground for some of the conjectures I'm going to introduce in a minute. So I should say that the dimension less than 8 restriction makes sense in the case of type 1. It's expected to be, if Mears conjectures hold, then you expect to find all of the Fano fourfolds that are toric complete intersections in ambient dimension less than 8, but it's definitely not true for quiver flag 0 loci. But that is, it does at least give you a finite place to look. So there's a program of a lot of mathematicians, including Al, but Corti, Coates, Galkin, Galish, Kasperchuk, Tveiten, and others, which is to use mirror symmetry to classify Fano varieties. And so, roughly speaking, the conjecture due to Al, whose name will keep coming up, and Tveiten, is that n-dimensional Fano varieties up to deformation should correspond to rigid, maximally mutable Laurent polynomials up to mutation. And these are Laurent polynomials in n variables. And we see that a Fano variety X is mirror to F, a Laurent polynomial, if the regularized quantum period is equal to the classical period, I'm going to explain all of these things in a minute. It's the classical period, the regularized quantum period. So the things that I need to explain. So I'm going to tell you what the quantum period is, what the classical period is, and what mutations are, and then what rigid maximum mutable Laurent polynomials are. And that will then give you a sense of what this conjecture is about. So the quantum period is a power series built out of genus 0 Gromov-Witten invariant. Here is a genus 0 Gromov-Witten invariant. It's a specific piece or slice of the J function, if you know what that is. And the classical period, the invariant on the Laurent polynomial side, is much easier to define, and you can define it as the constant term. So it's a power series, and the coefficient of t to the I is the constant term of x, f to the I expanded. So that's these two definitions here. And so now let me tell you what mutations are. So these are operations on Laurent polynomials, and they're compositions of two types, so of two things. So the first thing that could be a composition of is just a change of basis. So if you get a map from C star to C star, from C star to the n to C star to the n, coming from any matrix in GL and Z. And then F prime is just the pullback of F along this map. And then the more important part of the mutation is if you have some Laurent polynomial and one less variable, so on say Z1 to Zn minus 1, then we can define a rational map from C star to the n. That should be dotted to C star to the n, which I'll call VH, taken by sending Zi to Zi and Zn to H to the Zn when I is less than n, I equal to n. And then you can define F prime to be the pullback here. And this might not be a Laurent polynomial. But I'll say that F is compatible with this mutation. If the result F prime is a Laurent polynomial. So those are the equivalences here. And then the final thing to tell you is what a rigid maximally mutable Laurent polynomial is. So these are expected to be the mirrors of Fano varieties, smooth Fano varieties. So a rigid max mutable Laurent polynomial So first, let's let P be the Newton polytope of F. And you can think about F as being given by choice of coefficients on the lattice points of P. Then we see that a Laurent polynomial is rigid maximally mutable if it's compatible with a maximal set of mutations. And the coefficients are uniquely determined by this property. That's rigid maximally mutable Laurent polynomials. And so I want to tell you a little bit some of the evidence for this conjecture, which will be where the Laurent polynomials I want to construct for quiver flag 0 loci come in. So first, in type 1, if X is a toric complete intersection, then you can produce a Laurent polynomial F, which is essentially the Horry-Botham mirror combined with a change of variables called the Pre-Gelkowski method. And this method requires a technical condition called the existence of a convex partition. So a convex partition exists. In order to do this, but this doesn't turn out to be a problem at all when X is smooth in the search that Coates, Casper, Chick, and Prince did for all the Fano toric complete intersections of dimension 4. They were able to find a convex partition for all of them. And they also verified in the search that the mirrors they produced were rigid maximally mutable. And then the focus of the rest of my talk will be in type 2, the quiver flag 0 loci, which are the construction of conjectural mirrors, which I've found for 99 of the 141 Fano fourfolds I mentioned before. So I'm going to give you sort of an outline of how to construct them and tell you why I think this is good evidence for the conjecture. So let's suppose we have a quiver flag 0 locus inside a quiver flag variety. So if you want to construct a Laurent polynomial mirror of something which isn't a toric complete intersection, it's a good idea to try to take a toric degeneration. But it isn't so obvious, to me at least, how to take a toric degeneration of a quiver flag 0 locus. But if you look at the ambient space, quiver flag varieties share a lot of the properties with flag varieties, and so you can use some of toric degenerations of flag varieties are well studied, and so you can try to generalize some of those degenerations and then look and see what happens to the subvariety. So this is take a toric degeneration here. A particular one of the ambient space to a toric quiver variety, which I'll define later. But this is a generalization of the Gelfand-Cetlin toric degeneration. And then you can produce, by looking carefully at this toric degeneration, you can look at, you can produce a toric complete intersection, which I'm putting in quotation marks inside this degenerate toric variety. And so in other words, you can produce a set of divisors, but they might not be Cartier because it was a singular toric variety, but at least you have enough data to do the Pre-Gelkowski method. So you have something which looks like a toric complete intersection inside a toric variety, even though it isn't smooth. And you can still then do the Prijelkowski method. At least whenever you have a convex partition. Which was this technical condition I mentioned that you needed in order to do the change of variables. So if you do this, then you can get a Laurent polynomial with a Newton polytope. But it turns out that this is the wrong, in general, Laurent polynomial to take. What you need to then do is fix the coefficients of f prime to be rigid, max mutable. And you can do this using some code of L. And if you then fix the coefficients in that way, then you can get a Laurent polynomial, which you know is rigid max mutable because you've made it so. And it turns out that if you do this, whenever this method works, you get, if you compute 20 terms of the period sequence of the quantum period of the Fano variety, you can compare it with 20 terms of the classical period, and these turn out to be equal up to 20 terms at least. So there's no closed formula for the period sequence of Fano quiver flag zero locus, so you can't, it's not so easy to just check that they're equal to, but once you get to 20 terms, you're talking quite large numbers, so they're at least very likely to be Laurent polynomial nearest to the quiver flag zero loci. And so I think this is good evidence for the conjecture, because you exactly obtain a mirror only when you fix the coefficients in a way that makes them rigid maximally mutable. So the first thing, I want to explain this picture a little more. So the first thing I'm going to do is tell you about how to compute the quantum period of a Fano quiver flag zero locus, and then the second thing is I'll tell you more about this toric degeneration here. Are there any questions? Okay. So computing quantum period here. So this is done via abelianization, which is the first way of reducing something of type 2 to type 1, so reducing to a toric complete intersection from a quiver flag zero locus. So abelianization is quite general. So if you start with a GIT quotient where your group is not abelian, and you can look inside and take a maximal torus. And you have all of the ingredients you need to take a GIT quotient by the maximal torus instead. And if you say had a representation theoretic vector bundle on the GIT quotient, then, well, that's a representation. You started with a representation of G to get the representation theoretic vector bundle, but if you had, it's also a representation of T, and so you can get it to be, you can get a representation theoretic vector bundle on the abelian quotient as well. And so you can go from the subvarieties quiver flag zero locus to a toric complete intersection on the other side. So on the face of it, these two GIT quotients might not look like they have that much to do with each other. So for one thing, they are of different dimensions. But it nevertheless turns out that V mod T is, the abelianization is very useful. So there's results. I guess the first results were due to Martin and Elizabeth-Strom on cohomology, but there's also generalizations to quantum cohomology on I functions and J functions, and on Morey-Wall and chamber structure, looking at how the two relate. and others. And so the one that I want to mention here is for the I functions or the J functions, or for the quantum period is a specialization of that. But this abelianization is even nicer when your GIT quotient, you write that, nicer when your GIT quotient is a quiver flag variety, because then it plays quite nicely with the quiver combinatorics. So for example, if you have this GIT quotient here, this quiver flag variety here, so again, I've written the dimensions of the vertices next to the vertices, and I've written the number of arrows I mean by just drawing one arrow next to the arrow. If you want to abelianize it, it turns out you get another quiver flag variety, which you obtain by splitting up each vertex into the number of vertices that the dimension says. So you get one here, and then the middle vertex is dimension 3, so you replace it with 3, and then the last one's dimension 2, so you replace it with 2, and then you draw all the arrows you had before between them. And the dimensions are all 1. You can call this quiver Q, and then this quiver, you could call it the abelianized quiver. And so the T is quiver flag variety associated to the abelianized quiver. And so the theorem, which was a conjecture, which was also proved by Toric and Fontaine, Kim, and Saba for flag varieties, and then proved by myself for quiver flag 0 loci, and then proved generally by Rachel Webb for any GIP quotients of vector spaces, is the so it's the abelian non-abelian correspondence for I functions, but in translated in terms of what we need, it's the statement that you can compute the quantum period of a quiver flag 0 locus by computing the quantum period of the abelianization. And this actually allows you to compute terms, because this here is a toric complete intersection, and there's a closed formula, which is given Tell's-Mirror theorem for toric complete intersections, that allows you to compute terms of the quantum period of a Fano toric complete intersection. So that's the A side. And now let me tell you about those toric degenerations. So as I said, it's hard to find a toric degeneration of a quiver flag 0 locus of itself instead. And instead, what you should do is you should try to generalize known constructions for flag varieties. So what I'm going to do is I'm going to give you a description of the toric degeneration via a combinatorial object called ladder quivers. So I'm going to do this for not all quiver flag varieties, but for certain ones called Y-shaped quiver flag varieties. So let me tell you how to build them. So I'll start with the easiest case. So this is a ladder quiver, which I'm going to construct for any Y-shaped quiver flag variety, but I'll do it step by step. So the simplest quiver flag variety is something like this. So this is the Grassmannian Gelfand-Cetlin. And so the ladder diagram associated to the Ger and R Grassmannian looks like R, and this is N minus R. and then you add vertices. So these are internal vertices and external vertices. And then you orient this to make it a quiver by orienting paths like this. And so then the quiver you get has those vertices, and then the arrows between the quivers are paths you get by moving in those directions between the vertices. Like this, here, here, and one like this. This is the ladder diagram for the Grassmannian, and I'll call it LQ. This is Q here. And so then maybe the next easiest thing would be if you had another two-step flag variety. So it'd be you add an extra vertex with one path between them. So for example, like this. So this is the flag variety FL532, which sits inside the product of Grassmannians, GR53 cross GR52. And so points here look like C5 mod B1, C5 mod B2, and the incidence condition, which cuts out the flag variety, is that B1 sits inside B2. And so we can use this, so first to build the ladder diagram of the flag variety. So first we write down the ladder diagram of each of the Grassmannians. That's one like this. And one like this. And then we think of this incidence condition here as telling you that you combine this into the ladder diagram for the flag variety by modging them together like that. And then you have to add another vertex right here. And so you can, if you had a multi-step flag variety, you could just modge together a lot of the different, or modge together all of the different ladder diagrams of the Grassmannians in that way and get the ladder quiver or the quiver associated to the flag variety. And then now if you want to do this for something which is really a quiver flag variety and not a flag variety, well, you could do it for something like this, and I'll tell you how. So this is a quiver flag variety, like this. See? Let's call this Q. And so I told you at the beginning of my talk that this quiver flag variety can be thought of as a certain subvariety sitting inside a product of Grassmannians, where you had one for each non-source vertex, and that was the Grassmannian GR-NR, where N was the number of paths between the source and that vertex. So this vertex here has 5 paths from the source there, so that's GR53. Then the one with dimension vector 1 has 5 paths as well, so that's GR51. And then this last vertex here has 6 paths, so that's GR62. And so if we think of points here, if we label them as points like C5 mod B1, C5 mod B2, and C6 mod B3, then the incidence conditions defining the quiver flag variety are that V1 has to be sitting inside V2 and V1 plus C sits inside V3. And so again, to draw the ladder diagram of this flag variety, you draw the ladder diagram of each of the Grassmannian factors and then watch them together using these incidence conditions. Modging might go slightly less nice. Try 2 more. And so now you have something which looks like a flag variety. If you cover up one of these legs, you have something which just looks like the flag variety, but you've got two legs, so you have to put them out in different directions. So you put them out here. Maybe I'll redraw that slightly nicer, but you can see how they're overlaying each other. And so this is the ladder quiver here. And this process works. The recipe I've told you works for any Y-shaped quiver, which is one, that looks like this. So you only have two legs here. Choose ones, but I don't mind how many extra legs you then add after that, as long as the arrows between the vertices are only, I guess, of type A, and they only have one arrow between them. And then you can have as many arrows from the source as you desire. So the theorem is that there is a toric degeneration of a Fano Y-shaped quiver to the quiver flag variety, defined by the ladder quiver with stability condition given being the one that makes the toric variety Fano. And so the proof of this theorem, I won't tell you at all, is just, but the way you do it is by finding a Sogby basis of the embedding of the quiver flag variety inside the product of Grassmannians that I mentioned inside, and then you use the fluker embedding. So you can think of this quiver flag variety as sitting inside a product of projective spaces, and then you find a Sogby basis, and that gives you a toric degeneration. And so this is the embedding given by the vector bundles .wi. And so then you compare this. So the Sogby basis, once you found one, gives you a toric degeneration, and you can compare it with the image of the map of the ladder quiver inside the same product of projective spaces. And so this here is given by certain line bundles, and the line bundles, if I use this quiver here to tell you which they are, well, so let me draw the quiver here again too. So on this ladder quiver, if you think about it, you'll see that if you have any path in the ladder quiver, that gives you a V divisor on the ladder quiver variety. And so the ones that I want for the line bundles are the three that come from going from the top corner, from the bottom corner to the top corner of the Grassmannian pieces. So this path here, and this path here. So you can use these line bundles to embed it into the product of projective space, and then you can just compare the images. And so these, under the, when you match up these two varieties, you get an identification between the line bundles given by these paths and the .w1, the .w2, and .w3. Like this. And so now if you want to do mirrors for the subvarieties for general quiver flag 0 locus, you use this identification to figure out which divisors you want to plug into the Pre-Joukowski method. So this had been done before for flag varieties when the subvariety was a complete intersection, so cut out by line bundles, but you can also do it for vector bundles. So I'm going to scroll up to show a picture I wrote before the talk. So what you need to do is you need to express whatever the vector bundle cutting out your subvariety is via a splitting. So if you look at grade 6, sitting inside the product of projective spaces, the ladder diagram here looks like this. And I've told you that the path, any path you want, going from the source to the vertex I've labeled 1 in the picture corresponds to det, to B1. And so if you sum out all these divisors in this step, that's telling you that the tensor product of all the divisors here looks like O1 restricted to the ladder quiver variety, which is det W1. It's the same O1. And so then if you sum them, that gives you something which looks like a splitting of W1. So that gives you a bunch of divisors which sort of act like a splitting of W1. And then you can generalize this to Schur powers. So for example, by using, you can generalize this to Schur powers by writing the Schur power in terms of the Chern roots. So for example, if you had wedge 5 W1 plus det W1 twice on grade 6, then the picture you draw on the ladder quiver would give you 8 line bundles, or rather 8 B divisors, and the paths are the ones here I've pictured. So these 6 here are the ones coming from the wedge 5, and then the other 2 are 2 copies of dets. So that gives you 8 divisors on the ladder quiver, and then you can use the Pre-Joukowski method and then find the rigid maximally mutable ones in order to write down a mirror, and then you can check that this really does agree at least up to 20 terms. So in the last, I guess, 10 or so minutes of my talk, I want to talk a little bit about how this method connects with other mirrors for the Grassmannian. So are there any questions? Okay. So as I said, this method that I proposed produces only conjectural mirrors, except in one case, which is when your subvariety is actually the ambient space, and that ambient space is actually the Grassmannian, in which case the Laurent polynomial you get from doing this is the Gucci-Horry-Schoen mirror for the Grassmannian. So, for example, if you have Gur-4-2, then the ladder quiver, I've told you, looks like this. And so you could get the Gucci-Horry-Schoen mirror by running the Pre-Joukowski method on this toric variety, but it's usually described as a head over tail diagram, which is where you draw a sort of dual graph, I guess, to the ladder quiver. That is, you put vertices inside the boxes, and then you have an arrow crossing every arrow inside the ladder quiver. Oops. And then the Gucci-Horry-Schoen mirror can be described as, so you assign a vertex, you assign a variable to every vertex, and then you take the sum over all the heads of the arrows for the tails of the arrows, which is why it's called a head over tails diagram. And so that gives you a Laurent polynomial, which is the same or isomorphic to the one given by taking the ladder quiver and running the Joukowski method on it. And so a theorem so the reason why we know that this actually is a mirror, that does compute the period sequence of the Grassmannian, is a theorem of Martian reach, which says that, that the period sequences agree. And this is a corollary of their results on the Fluker coordinate mirror. Which I'll call WP. So I want to tell you what WP is, but I want to tell you, I guess, motivate it. I mean, maybe not the original motivation, but give you a sort of motivation by telling you about another mirror for the Grassmannian first, which is due to Gu Sharp. So, and this is kind of closer connected to abelianization. So if you consider the abelianization of the Grassmannian Gur-4-2, so this works for any Grassmannian, but I'm just going to use the smallest example, that's P3 cross P3, which has weight matrix like this. And so the mirror looks like this. And so if you now set, so this has too many quantum parameters to be the mirror to the Grassmannian, but there's a well-known way for solving this problem coming from, for example, the original conjecture of Trocken, Fontaine, and Silva, which is that you can specialize them by setting Q1 and Q2 equal to just one quantum parameter, the negative because 2 is even, and which we think of the quantum parameter coming from the Grassmannian. And so once you make the substitution, this is the Gu-Sharp mirror, or a big part of it. And this really is a mirror because its critical locus computes the quantum cohomology ring of the Grassmannian, which I think is really cool, but only if one asserts that x is equal to y. So, or x is not equal to y, sorry. So on the critical locus, the xi's and the y's turn out to be the same, and so you say that the x is not set, then you can say xi is not equal to yi. In other words, you can divide by this in the ring, and once you allow that, you can compute the quantum cohomology ring of the Grassmannian using this mirror, specialized mirror of the product of projective spaces. But from the perspective, I guess, of the conjecture, this mirror has too many variables. It has 6, the Grassmannian is only in dimension 4, and so how would you possibly, like, what can you do to make this into a mirror in the correct number of variables? And so Martian Reach have an answer to this. So let me just tell you what it is by first observing that if you look at these columns here, so x1 plus y1, x2 and y2, x3 and y3, in this column here, you can think of each column as can be thought of as a way of writing O1 plus O1 here, sorry, O1, 0 plus O0, 1 here, or rather O1, 1, I guess, if you think of them added together, which is under the abelianization, the first Chern class of Q. And so what the Marsh-Reach mirror does is saying, well, we don't know how to do this for these variables, but we can do this using the quantum cohomology ring. So think of using the quantum cohomology ring to write C1 of Q 4 different ways, and then see what happens, but use 4 different ways coming from quantum Pierre rule. So let me just tell you this fact here. So the cohomology ring, quantum cohomology ring of the Grassmannian is generated by symmetric polynomials, sure polynomials, indexed by partitions, where we say the partition fits inside an R by n minus R box. So for example, for Ger42, you have S1, S box, S11, S2, S21, and then S22. And so you can use quantum theory to write down equations like this. And so then what Marsh and Reach say, or proposes, the mirror, the Kluger coordinate mirror, is to write down S box, which is C1 of Q, more times using these rules instead of the one you get from abelianization. So that would be S box over S empty set plus S21 plus this one plus Q S box like this here. And so that's not the actual mirror. And so then instead, what you do is you use the fact that these partitions here also index subsets of size R of 1 to n. And so the way you go between it is looking at where the vertical steps happen when you think of this as sitting inside the 2-2 box. But suffice to say, you just write it like this using Kluger coordinates. And then these Kluger coordinates they're not algebraically independent, and so you can use the relations between them, the Kluger relations, and you can make choices and then choose ways to write them into the correct number of variables. So this is one such choice. And in general, the choices are given by the cluster structure of the coordinate ring of the Grassmannian. And one of these gives, one choice gives the EHX mirror. And for the Ger42, it's this choice here. And so if you look at what happens when you make this substitution, then each of these either split or don't. So this one will split into 2 monomials, and this one will too. And then these will just stay as 1. And then then you look at how this matches up with the EHX mirror. It works like this here. So this W please splits up, as I said, so this is into 2, 2, and 1, 1 here. And then you match it up with the head over tails according to the color code I gave you. So they match up in terms of the columns and the rows of arrows. And so let me just look at the purple one for a minute here. So this purple one here, you can see that it's the sum of this arrow here and this arrow here in the EHX mirror. And if you look at the dual version for the ladder diagram, that's this arrow here and this arrow here. And so if you did this for any Grassmannian, what you'd see is that this process, due to Reach and Marsh and also Laurent Williams, of going from the Kluger coordinate mirror to EHX, you think of each of these monomials, which represent S box, as splitting into R and minus R1 monomials, and that exactly matches up with the way I described of splitting Q, the tautological bundle, or an S dual, splitting into paths here, which are the way I proposed for finding mirrors of the quiver flag 0 loci. And so if I think I have 1 more minute, because I started a bit late, which is I just want to say that in work in progress with Wei-Gu, what we're trying to do is we're working on writing down Kluger coordinate sound mirrors for the flag varieties, and then also less successfully for other quiver flag varieties, but we can do this for examples. And so in these examples, you can use the supercoordinate mirrors we're proposing to find Laurent polynomial mirrors, not just to the ambient spaces, but also to the quiver flag 0 loci. So for example, there's these four folds here on this quiver flag variety. So these are 4 of the 99 that I know how to find mirrors for using this other method. And then what we're able to check is that if you start with this quiver flag variety and one of these vector bundles, you can use either the Gelfand-Cetlin degeneration to find a Laurent polynomial like this, or you can use the Plicker coordinate mirror and specialize it until you find another Laurent polynomial. And these are not isomorphic, but thanks to code, again, of Al, we can check that these are mutation equivalent through a series of 4 or 5 mutations. And so these two mirrors, both conjectural, but computed during completely different ways, must have the same period sequence. That's where I'll end. Sorry for going a couple minutes over time. Thank you.